आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज।
What if rocks could talk? Dr. Subham Bose from the WIGH Institute of Himalayan Geology listens using microtectonics and metamorphic secrets to reveal the Himalayas' epic billion-year story of collision.
I'm Dr. Subham Bose from the WIGH Institute of Himalayan Geology, Dehradun. I did my PhD from the Department of Geology and Geophysics in the Indian Institute of Technology, Kharagpur, under the supervision of Professor Saibal Gupta in the broad field of structural geology and tectonics. After that, I joined the WIGH Institute of Himalayan Geology for a postdoc, where I continued for about 1 year, 2 months, and after that I joined this institute as a scientist B. From April 2022 till date, I am working in the WIGH Institute as a scientist B in the structure and tectonics group. So my broad research area is structural geology and tectonics. If I go into further details, I work on structural geology, microtectonics, rheology, and fundamentals of metamorphic petrology.
Okay.
We have the tectonic plates on the surface of the earth. So two of these plates are the Indian plate and the Eurasian plate. Now these two plates collided at they actually bumped into each other at about 55 to 50 MA, that is million years from before present. And this collision is going on even at present. So due to this collision, we have some deformations both in the Indian as well as the Eurasian plate. So this collision actually formed the Himalayas, and because of this collisional forces, we have some large scale deformation as well as some small scale deformation in the interior of the Himalayas, and this gives rise to huge strain within the Himalayas, which actually forms some major discontinuities, like we have the main boundary thrust, the main central thrust, the South Tibetan detachment, and of course we have the Indus Sangpo suture zone, where along which the two plates, that is the Indian and the Eurasian plates, actually collided. Now this collisional forces are affecting the Himalayas, and because of this, different levels of the Himalayan crust are deforming in different manners. So I am particularly interested in the middle part of the crust that is ductile in nature, and that is undergoing some extrusion due to crustal thickening because of this compressive forces. These compressive forces are basically making a pile, that is, we are having the Himalayas, and in the middle crust and the middle crust of the Himalayas, in presence of the weight of the overburden, that is undergoing some extrusion. So I am interested in studying the mechanism of this extrusion. So we have both frontal extrusion as well as lateral tectonic escape. We have sidewise flow of material, as well as we have the flow of material towards the south, that is towards the Indian plate. And this extrusion mechanisms are actually controlled by the strain regime, that is, the forces cause some strain. That is, if we have stress, we will definitely get some strain. So this strain regime actually controlled this extrusion mechanism. So I study the strain regimes, and using those strain regimes, I understand the vorticity of this mid-crustal flow, and then I try to understand, integrating this data, I try to understand the mechanism of extrusion. Now this is also being done in the upper part of the crust, that is in the top 10 to 15 kilometers, where the extrusion mechanisms can be inferred or by analyzing earthquake data. we have earthquakes, so we can analyze earthquake data, and actually we can infer about the present day strain field. Of course, and that will date back to maybe some 50, even to 50, 60 years back. That is the decadal strain field. We can address it, and that strain field also tells us about the extrusion mechanism that is going on. But of course, there is some difference in the material behavior between the upper crust and the middle crust. That is, the middle crust flows while the upper crust has more of a elastic nature, because of which we are having the earthquakes. But not only because of elastic nature, we have deeper earthquakes due to the presence of fluids that actually trigger earthquakes even at greater depths. Okay. The Earth's crust is made up of tectonic plates. There are several tectonic plates. Two of them, I didn't say two types, but two of them are the Indian plate and the Eurasian plate. Similarly, we have different other plates also. We have the Pacific plate. So these are just the names of the plates. Okay. So the collision between the Indian and the Eurasian plates form the Himalayas. During my PhD, I worked on the deformation mechanisms in the northern part of the Eastern Ghats belt in India. So there actually I tried to address the deformation kinematics, the dynamics, the mechanism, and the rheology of deformation along the different shear zones. Some of these were penetrative, some of these were localized. We had strain partitioning at different scales. So we also find out a way to determine qualitatively the high strain rate and the low strain rate zones, that is the zones where strain has accumulated at a higher rate and the zones where strain has accumulated at a lower rate, directly from the field by using stretched minerals, which actually are referred in geological literature, those are referred to as stretching lineations. So using those lineations, we actually found out a way to determine which zones have deformed at higher strain rates and which have deformed at lower strain rates, although qualitatively. So we are in a process of improving it and quantify this as much as possible. So this is I also worked on solving the discrepancies between the deformation geometry that are inferred from satellite imagery and the deformation geometry that is observed directly on the ground while studying the rocks. So we found that it's not always what we see on satellite imagery is not always the case. So the sense of motion can be very different. So actually in my study area, some reorientation of fabrics and lineaments occurred, which was initially inferred to be due to some lateral movement, whereas we suggested that, based on our detailed field studies, we suggested that reorientation is just an apparent sense, and that reorientation is due to some vertical movements. So this is what I did during my PhD. Following that, during the tenure of my postdoc in the WIGH Institute of Himalayan Geology, I started working in the Karakoram terrain that comes in the Eurasian plate. So there I worked particularly on the Karakoram granitic batholith and deciphered, or rather I reconstructed its exhumation path from the time and depth of its crystallization. And I also inferred a decline in order of strain rate by an order of 10 to the power 2, rather a decline in strain rate by an order of 10 to the power 2 during the cessation of collision along the Shiok suture zone. So the Shiok suture zone is basically the zone along which the Ladakh batholith, the Ladakh granitic batholith and the Eurasian plate collided. So after that, I joined the WIGH Institute as a scientist B, and here I mainly worked on and I'm still working on the deformation mechanisms along the major lithotectonic discontinuities, like the main boundary thrust, the main central thrust, the South Tibetan detachment zone in the western part of the Himalaya. I have worked in the Garhwal. I am working in the Garhwal Himalaya as well as in the eastern Himachal Himalaya. So There I am trying to address the extrusion mechanisms both in the middle as well as the upper crust, and this extrusion mechanisms has some direct implications for the society as well. So basically, I try to reconstruct the strain field from the strain field inversion of earthquakes, and using that we can actually say which orientation of planes has the most potential to undergo slippage, maybe during an earthquake or due to tectonically induced landslides that may not be necessarily due to earthquakes, but due to some increase in pore fluid pressure along an already stressed region, that is a region which is under some force. Structural geology has several aspects. We have the very fundamental geometric aspect. Just we go to the field, we find the planes in the rocks, we have the beds and the foliations, and we just study their geometry. So if we talk about the geometric aspects, India has done a lot in that already. Okay, and both in the Himalaya as well as in peninsular India, we have lots of works that have very well addressed the geometry of the rocks. If we now come to the kinematics, that is the movement along zones which produce these geometries. So these kinematics have also been studied, but there are still many areas where this has to be studied, or these are yet to be studied. Now, if we come to the deformation mechanisms, where we characterize the type of flow, that is the type of deformation, by integrating the strain data with the kinematic data, then I would say that there are still much to do, particularly in the Himalaya as well as in other parts of the country.
Okay. Also, if you want to tell us about some of your research papers being published in different journals.
Yeah. So during my PhD, I have published 4 papers. So 2 of those were in the Journal of Asian Earth Sciences. So it had an impact factor at about 2.7 to 2.8 back then in 2018 to 2020 during this period. I also published a paper from my PhD work in the Journal of Structural Geology, so which had an impact factor of about 2.7 to 2.8. We had a paper in Precambrian research that is also partly from my PhD, so that had an impact factor of about 4. So after that, after joining Wardia, I got a paper in polar science that then had an impact factor of about 1.5 to 2. After joining Wardia as a scientist, I got a paper in the International Journal of Earth Sciences, which had an impact factor of about 2.7. And last year, in 2024, I got a paper in the Journal of Structural Geology again, and it had an impact factor of about, say, 2.8 to 3 then. Thank you for paying attention.
This podcast series on STEM popularization is supported and catalyzed by National Council of Science and Technology, Communication, Government of India. Produced by Media for Community Foundation. Technical support is given by Soumya Mishra.